So far, we have learned about the layered perceptrons or layered neural network. The next talk by Dr. Niebuhr is on Kohonen's self-organized network. This type of neural network is suitable for clustering data into several classes. It is also powerful for applications where the output data is not available or is smaller in size than the input data.
In my next talk, I'm going to give an example of unsupervised networks. I will talk about Kohonen's self-organizing feature map. More in detail, I will show you the Kohonen self-organizing algorithm. I will talk about some properties of the maps, and I will give some examples. And in the second part of the talk, I will give an overview of technical applications, and I will go more into detail into the application of transformer fault diagnosis, electric load forecasting, and power system security assessment. Kohonen's is a Finnish mathematician who has done a lot of work in the modeling of biological neural networks, and actually he got his inspiration from work done by Rasmussen and Penfield on the somatosensory cortex. What you see on this next slide is a two-dimensional representation of the somatosensory cortex of the human brain. The human brain usually has in the order of 10 to 11, 10 to 12 neurons, and roughly 5% of them are allocated to the somatosensory functions, functions which feel, which grab. And as you can see on this map, neurons in certain areas are associated to certain functions. We have neurons allocated here which are responsible for somatosensory signals coming from the foot, coming from the knee, the hand, the face, and the mouth. And as you can see, these areas are not equally represented. As you know, as human beings, we are very vocal, so we use our speech, we use our mouth, our facial expressions also very detailed, and so there are much more neurons allocated to our face or to our hands than to our feet. Actually, there is work done at the Salk Institute which looks at the allocation of neurons in case we are losing some of our members. And what they find is that if you lose your hand, then your neurons might be allocated to other areas of your body. And so your brain is capable of readapting to the outside environment. So this figure has been reprinted with permission by Simon and Schuster from the original work of Penfield and Rasmussen in 1950. And as I said, as engineers, we are going to simplify our neural model considerably. The somatosensory cortex has several billion neurons. Now, what we are dealing here on this slide is we are reducing it to 16 neurons, which in the case of the feature map are arranged on a grid. And we have our input layer, which has dimension 3. Each component of our input vector is connected to each neuron on the grid. So our weight vector has the same dimension as the input vector. On the grid, we are going to define some sort of neighborhood relationships. And for example, we can say that if the weight vector of neuron 9 is the most similar to our weight vector x, then neuron 9 will be called the winner or the neuron of order 0. And we have neighbors of order 1, which are neuron 8, 10, 5, and 13. Neighbors of order 2, which are neuron 12, 14, 11, 6, 1, and 4. Neighbors of order 3, which are neuron 15, 7, 0, and 2. And one neighbor of order 4, which is neuron 3. Now, this definition of neighborhood is arbitrary. We could have chosen 8 neighbors of first order by just selecting all neurons on this square to be first order neighbors of neuron 9 and all neurons on the border here to be second order neighbors. So we have some choices in the definition of the neighborhood. And we have already talked about similarity measures. So in our case, neuron 9 is called the winner for input vector x if the difference between the weight vector of neuron 9 and x is smaller than the difference between any other weight vector and our neuron x. We also can now establish a neighborhood function. This neighborhood relationship can be expressed in the form of the function. Originally, Kohonen has chosen the Mexican head function as the function defining the neighborhood relations. And actually, in this slide, we will see that we have excitatory positive connections for neighbors of first order of our neuron, and we have inhibitory negative connections for second and third order neighbors of our winning neuron. This Mexican head function can be expressed as the difference of 2 exponentials, and it has a large potential for parallel implementation. The other choice, which is usually used for sequential implementation, is the Gaussian neighborhood function. In this case, we do not have any inhibitory connections between neurons, but our connection strength will go to 0 for neighbors which are very far away from our winning vector. We can express this by an exponential of the coordinates of our winning vector and our other neurons. And the width of this Gaussian function is given by our function sigma, and sigma is decaying with time. So at the beginning of our training, we will start with a very large neighborhood. A lot of neurons will learn about the new incoming input. As our learning progresses, our width will shrink, and at the end, only the winning neuron will learn something about the input. So let me give you the algorithm of the unsupervised training. This algorithm is due to Kohonen in 1982 and is often called the self-organizing algorithm. At time t equals 0, we are going to initialize our weights randomly, and we are going to choose our input vector x randomly from the set of training vectors. We are further determining our neuron I star such that the Euclidean difference between the weight vector of neuron I star and x is minimal. We are going to update the weight vectors omega I star of neuron I star and its neighbors I by the following procedure. Our new vector I star is equal to omega of I star at time t plus the product of our learning rate times our neighborhood function times the difference between our input vector and our weight vector. We are then going to increment our time step t, and if for several time intervals our algorithm stays stable, our weights do not change, then we are going to stop, otherwise we are going to step 2. Let me try to illustrate this procedure for a very simple Kohonen network. In this case, our neurons are arranged on a string instead of a grid. So we have a one-dimensional neural network instead of a two-dimensional neural network I've shown before. And we have a two-dimensional input vector. So this is the first component of our input vector, the second component of our input vector. Now, let's assume we draw one input vector randomly at this point in our two-dimensional plane. Then the nearest weight vector is the weight vector of our yellow neuron. Our neuron is placed at the coordinates of its weight vector, and its neighbors are defined by being the neighbors on the string. Now our updating rule says that I have to move my weight vector in the direction of the difference between input vector and weight vector. So I'm moving it along the line, and my learning rate eta and my neighborhood function lambda will indicate the size of the step I'm making for this neuron towards my input vector x. And since our neighborhood function is shrinking, the neighbors of first order will be moved also in the direction of the difference between input vector and weight vector, but at a smaller pace than for the winning neuron. And in the example I'm showing here, neighbors of second order are no longer updated because I assume that my neighborhood function lambda is very small. The following slide will show schematically how the self-organizing process functions. I'm assuming here that I have a 10 times 10 Kohonen network, and so I have 100 neurons. These neurons are placed in the plane at the coordinates of its weight vectors, and if I initialize my weight vectors randomly, I will get a very scrambled picture. So the points you see on these pictures are the randomly initialized weight vectors of my 100 neurons. After 200 steps, our Kohonen network is already topologically ordered. You can see already that we have some sort of neighborhood relationship maintained for our map. And for 1,000 steps, we have a good representation of our input space. We have trained our neural network with uniformly distributed two-dimensional input vectors. And as you can see, after 1,000 steps, our weight vectors are also uniformly distributed in our two-dimensional plane. This is actually one of the important features of the topological feature map. It conserves the probability distribution of the input vectors. Actually, it will oversample underpresented input vectors and undersample often presented input vectors. But in general, it gives you a very good distribution of your input vectors. And so what I'm showing on this next slide, my input vectors are no longer uniformly distributed, but Gaussian distributed. And as you can see, then our 10 times 10 feature map does not represent our two-dimensional space equally spaced, but it will present areas where we will find a lot of input vectors with more neurons than areas where we find less input vectors. What we see in this slide is the Voronoi tessellation of the input space by the Kohonen network. And so if we look, for example, at this neuron, it will classify all input vectors which fall into this class given by the black lines. Once again, we will have fine small classes for regions where we have a lot of input vectors and large classes for regions where we have only a few input vectors. So what are the properties of the self-organizing map? We have data quantization and feature detection in the n-dimensional input space. We have conservation of the probability distribution of input vectors. We have prototype generation. Weight vectors represent classes of input vectors. And we have topological organization of the map, that is, vectors close to each other in the input space are represented by weight vectors belonging to neurons close to each other on the map. Let me now give you an example in the three-dimensional space. In this case, we have a 4 times 4 feature map, three-dimensional input vectors and three-dimensional weight vectors. Once again, we are placing our neurons at the coordinates of their weight vectors. And this small map has been trained with 5,000 vectors uniformly distributed in the cube of length 1. And as you can see here, after 5,000 steps, our 16 neuron map will distribute inside the cube, and all neurons in this part of the cube will be classified by this corner neuron. All neurons the red dots in this part of the cube were classified by another corner neuron. Input vectors being in the middle of the cube will be classified by the inner neurons of the map. This Kohonen network has been used by Pierre Desmartins from the Swiss Federal Institute of Technology in 1991 for the classification of geopolitical data. In this case, our input vector is of dimension 6. And the first component of the vector denotes the economic growth of a country. Second vector, the infant mortality. Third component, percentage of illiteracy. Fourth component, the school attendance rate. Fifth is the gross national product. And sixth is the growth of the gross national product. He has taken data of 52 countries. Actually, the data is a little bit older. I think it's from '88. And the data was centered and normalized. And he trained an 8x8 Kohonen network in 20,000 iterations. After these 20,000 iterations, he looked at the weight vectors of the Kohonen network and identified which countries have been classified by which neuron. And actually, this distribution is very interesting because, as you can see, very rich countries like Switzerland and Sweden have been classified by one neuron. You find the large G7 as neighborhood neurons of Switzerland and Sweden. So here we have France, the Federal Republic of Germany, the USA, Canada. We have Italy in this part of the map, while Ireland, Spain, Finland, the UK. We find the communist countries are regrouped together. At that time, in '88, we still had the German Democratic Republics, the Soviet Union, Cuba, Chile, Poland, Hungary, and Vietnam, Nicaragua. We find some of the Islamic states like Indonesia, Turkey, Algeria, Morocco, Senegal grouped together. Some of the African countries are grouped together. Here we find the very rich oil countries. And at the other end of the map, we will find the Sahel states, which are really one of the poorest regions on Earth. So our Kohonen map was ready to able to identify important features of our 6-dimensional input vector and represent them on the 2-dimensional map. There is a lot of work done on the theory of Kohonen networks, and it's far from being solved. Let me quote you some of the important results, which have unfortunately been proven only for low-dimensional input vectors. The first example is, the first result is that for a 1- or 2-dimensional probability distribution of input vectors, the weight vectors will converge stochastically towards stationary states of the system if the learning rates obey the Robbins-Monroe conditions. The Robbins-Monroe conditions specify how fast the learning rate will go to 0. And this is work which has been done by Kohonen in '84, Cottrell-Ford in '86, and Ritter and Schulten in '88, and Dillon in '91. For the 1-dimensional case, we have a convex neighborhood function, and for the topologically ordered states are the only stationary states of the system. This is work done by Erwin, Obermeier, and Schulten in '92. And what they basically say is if we have a convex neighborhood function, a Gaussian function would qualify as a convex neighborhood function. We cannot have a distortion of the map. For continuous probability distribution in the 2-dimensional case, we have a negative result. There is no energy function whose minima correspond to the stationary states of the system. This is an important result because for continuously distributed input vectors, we cannot use classical optimization techniques to minimize an energy function because there is none. However, for discrete probability distribution, we know that the algorithm will minimize an energy function and that the self-organizing algorithm converges stochastically to stationary points of the system, work done by Ritter and Schulten in '88 and Rusica in '93. Let me now go to an overview of applications. The first application was published, or one of the early applications was published by Kohonen himself in '88 for phoneme classification of phonemes of the Finnish and Japanese language. Semantic maps were also published by Ritter and Kohonen in '89. Martinez and his co-authors did work on visual motor coordination of a robot arm in 1990. Chaotic time series prediction was done by Walter in 1990. The traveling salesman problem has been attacked by several research groups. Argeniol in '88, Favata in '99, actually Ford in '86 already did work in this area also. Process classification and control by Treba and Goza in '91, image compressing by Nasrabi Fang in '88, and for power system I would like to refer to our publication from 1996, where we have listed a large number of references. Actually, more than 1,000 references are available from a website or an FTP site at the Helsinki Technical University. Let me now go to some applications of the self-organizing feature map to power systems. The first application I would like to cite is the work done by Thomas Baumann and Alain Germain from the Swiss Federal Institute in 1991. They were training the Kohonen classifier for transformer diagnosis. Basically, they have established 56 training cases and 28 weight vectors, and these were given by the transadmittance of a transformer, actually by the Fourier transformation of the transadmittance of the transformers. And so their database are basically some sort of curves. They were discretizing these curves. They were training a neural network. And since these transadmittance functions corresponded to normal or faulty behavior of a transformer, they fell into one of the classes established by the neural network. And so for an unknown input vector, one of the classes would respond in saying, I'm the most similar class. And this class then would correspond either to a no-fault situation or to fault 1, fault 2, fault 27 situation. They achieved pretty good classification errors in the order of 1 to 2%, depending on the network size and the selection of the training vectors. And if you look a little bit more into detail on how these input curves are represented by the Kohonen map, you can see that there is a certain relation between these discretized inputs and their neighbors. If you look, for example, at neuron 27, you can see that it has 2 peaks. And if you move to its neighbors, you will see that, for example, neuron 35, the first peak is more pronounced, the second peak becomes leveled out. If you go to neighbor 28, you see that the second peak gets leveled out, but the first peak stays constant. And if you have a closer look at the other neighbors of neuron 27, you can see that they are similar to neuron 27, but not exactly the same. So once again, the Kohonen map is able to map a 6-dimensional input vector on a 2-dimensional map. The second example I would like to talk about is the use of the self-organizing feature map for the prediction of electric loads. We usually have problems in classifying the climate differences, tropic versus Arctic, maritime climate versus inland climate. We have geographical differences, rural versus urban region, mountains versus plains. We have seasonal differences, summer air conditioning during daytime, winter heating during evening and morning hours. We have daily differences, we have holidays versus weekdays and weekends, customer differences, household versus industry, and social difference, church going versus soccer games. And the further problems are stochastic load behavior and weather forecast. So electric load forecasting is a complicated statistical estimation problem. And I'm citing here work done by Germain, Macabre, and Baumann in '92, who have trained a neural network with the following input vector. They have used the 24 hourly loads 4 day-type classes, Monday, Tuesday to Friday, Saturday and Sunday, 3 different meteorological data, temperature, humidity and cloudiness, and the load at noon for the next day. So they had 32 input vector components, and they were, during training, they were looking for the nearest weight vector for all 32 input vector components, and they were updating all 32 weight vectors. For testing, of course, they did not have the load of the next day. And so for testing, they were looking at the nearest weight vector for the first 31 components. They left out the 32nd. And as the 32nd component, they took the 32nd component of the weight vector as a predictor for next day's load. If you look at the organization of Kohonen's feature map, it is really very nice. You can distinguish here the different day type classes. We have Mondays regrouped in this region of the map. We have Sundays in this region, Saturdays, and here we have the weekdays. And we can further distinguish neurons which classify summer data, winter data, and spring and fall data. So our Kohonen map gives us a pretty good two-dimensional picture of the different types of load data we are encountering during the process. And the map was trained with 1 year of data, all days included, from 1985. The test data was 1 year, all days included, 1986. And the results were good root mean square error in the order of 3%, but bad maximum error in the order of 13%. And the remedy is data clustering with neural networks, but afterwards fine-tuning for each class with a supervised learning algorithm. This work has been done by Piras and his co-authors in 1995. Actually, it is not very astonishing that prediction was not successful with Kohonen networks, because the weight vector will be the average of the class. However, if you're doing peak load prediction, you would like to go to the edge of the class. However, for classification, this is a very nice application. And I would like to thank Lawrence and Earlworm for providing the slides of this application. The last application I would like to talk about is power system static security assessment. Once again, we have the operating space of our power system, which we have already discussed in the previous talk. And we are going to quantize our operating space by our cubes, and we will place the neurons of our Kohonen map in the centers of our small typical parts of our security cube, and then we can label our neurons according to our cube. So we have our blue neuron here, we have a green neuron here, and a yellow neuron here. And depending on where the weight vector of our neuron is located, we will have a secure neuron where the power is a similar size for all lines. We will have a secure neuron, but the power for line BC is small. We will have a secure neuron where the power for AC is small. And if we go then to the borders, we will have some pink and violet neurons, which will be critical for certain lines. And we will have an unsecure neuron here, which is red, where the limit is exceeded for line AB. And our white neurons actually are all unsecure, and I did not specify which class, which specific lines limits are violated. So if we then take this map and stretch it out on a two-dimensional plane, and if we keep the color coding of our neurons, we can still distinguish our secure neurons, our critical neurons, and our insecure neurons, which include the white neurons. And I have now taken the same concept for a larger power system. In this case, we have a 5-bus system, 7 lines. I have trained a 7x7 Kohonen network with 46 training vectors, which I've presented several thousand times. And what this map shows is the classification of 184 untrained vectors. So these are my test vectors. And actually, as in the case of the 3-bus system, my map here distinguished different cases. in this area of the map, we will find outages of line north-south, usually resulting in overloads of line north-lake. In this part of the map, we will find outages of line north-lake, usually resulting in overloads of line north-south. In this part of the map, we will find islanding cases where we have isolated one of the buses due to a double contingency. And in this map, my white neurons actually correspond to the normal cases where we might have outages but no overloads. So once again, we get a pretty good two-dimensional picture of a 40-dimensional operating space. And the Kohonen network is able to successfully classify test vectors as had not seen during the training set. Let me come to the conclusion. As an acknowledgement, I would like to acknowledge the following publishers: Simon & Schuster, Lawrence Earlbaum, and CRL Publishing Ltd. have all three provided figures previously published with them, either by me or by some of my colleagues. And in conclusion, I would like to say that the Kohonen self-organizing map achieves quantization of input vectors into a finite number of prototypes of typical vectors. It achieves projection of similar points to neighboring clusters and different operating points to different regions of the feature map. It achieves generalization. Clusters established during training can be extended for input vectors not belonging to any trained category, and so we have successful classification of untrained input vectors. The Kohonen network can be used for prediction of input vector components, although it will go to the average of a class, not to the border of a class, and it can be used for a graphical representation of class information of an n-dimensional input space on a two-dimensional map. Thank you for your attention.